Math that matters. Welcome to another edition. CT-4, Statistics and Critical Thinking, Lesson 4. I'm doing this from the upstairs room in my house. There's literally a hedgehog named Bartholomew right there, right there. Not supposed to touch it though. I don't think I've ever touched Bartholomew. I've been warned. They stick their little quills out. Yeah, so it's a little warm in here, a little different room, but thought I'd give you a different look. So today won't be probably the easiest thing we've done, but it's really interesting. It's really cool. It's fascinating. We're looking at some principles of statistics, but really more probability. So today we're going to look at what's called Bayes' theorem, and you'll need to remember the conditional probability formula from the last lesson, which I'll bring up. You also need to remember that when our operator is and, that means to multiply. So we're going to have some probabilities today that we're going to need to multiply together. And when your operator is or, as long as you have mutual exclusivity, as long as there's no overlap, then we can add probabilities. So we're going to need all of that. Conditional probability formula, the and the or operator. And we're going to bring this into a context and look at what's called the base rate fallacy. So it's kind of like it's a paradox, which means that there will be situations and problems that we have, and we'll expect a certain answer, but the math will show us that our expectations aren't in line with reality, which is pretty interesting. So let me run you over to my PowerPoint. As always, I think you're going to love this because super interesting, cool stuff. All right, so Bayes' theorem, we're going to look at testing. And again, as I mentioned, a statistical paradox or a probabilistic paradox. And there's this little cartoon where the doctor's looking at the guy in bed and he says, our statistician will drop in and explain why you have nothing to worry about. So what we're going to look at today is testing, test results. And it can be, usually in the textbooks, it's disease testing. So we'll talk about disease testing, but it can be any kind of test. I also have a car alarm problem today. So anytime you have something that is supposed to give you information about a positive or a negative result, and so you could get a test for a disease, you might test positive, you might test negative, but we have to consider that those results can be accurate or they can be wrong. And what do we do with the way in which the possibilities arrange themselves and the probabilities that align in the directions of those arrangements? Now, this is what Bayes' theorem looks like in the textbooks, and this is probably scary to you. What you really don't need to worry about is pretty much any of this. We'll just use our conditional probability formula from the last lesson, which says the probability of A, given that B is true, equals, really it's just the probability of A and B divided by the probability of B. This simply says the probability of B given A times the probability of A, but that's probably not going to be the best way to understand it. So we'll write it differently. And down here, the interesting thing about this is that there are just several possible ways to get to a world of B. So B is some sort of given condition that we know is true, but there might be multiple ways to get to the world of B, and we're going to have to consider that. And making a diagram is going to be critical to understanding what we're going to do today. There's really only one kind of problem, but it's kind of tricky. I think to illustrate this, so this is in our textbook, our logic textbook, I'll give you this example. So in this example, there's a building with 3,000 people in it. And suddenly they make this announcement. They say, there's a terrorist in the building. We're going to shut down the building. We're going to close all the doors, lock everybody in, bring all 3,000 people to the front. And we have this machine, and this is a hypothetical, but this is a machine that we're going to just like, I don't know, some sort of truth serum machine or whatever. We're going to test every single person one by one. And this machine is like a 90% terrorist detector. So they test the first person, they test the second person, they test the third person. Remember, there's 3,000 people in the building, and we've got a 90% accuracy on our tester, which means, if you think about it, if we have one terrorist in the building, but we test all 3,000 people, there's a 10% error rate on this tester, which means there's actually, if you think about it, 10% of 3,000 is 300. So what that means is, even though 90% seems pretty good, the 10% that it's wrong in will amount to about 300 people. So if you think about it, if there is one terrorist out of the 3,000, but we have 300 people that test falsely, as the test says they're a terrorist, but it's not accurate, that means there's this one terrorist, and then there's 300 other people that are identified by the machine as terrorists. So there's actually only one terrorist out of 301 people identified as terrorists, assuming that the actual terrorist is identified positively. And so the crazy thing about that is, if you think about it, 1 divided by 301 is actually this 0.3%. So if you are identified by this machine as a terrorist, there is 1/3 of 1% chance that you actually are, which seems crazy because it seemed like we've got something that's very accurate. Now we could even change the rules a little bit. Let's say we had a 99% test that was going to give us with 99% certainty, when it tested, it would find the terrorist with 99% accuracy. But if you think about that, and you can read through my slide, I'm just talking through it, but the test is 99% accurate, see down here. So if we change it from 90 to 99% accurate, you think, oh, we're really going to be pretty strong in our ability to say something about whether or not, if a test comes out positive, if this person's actually a terrorist or not. But if it's 99% accurate, that means it's 1% inaccurate. So 1% of the people who are tested by this device will test as terrorist, but not actually be terrorist. And 1% of 3,000 is 30 false positives. Assuming that the actual terrorist is identified, that means there would be 1 terrorist out of 31 people identified as terrorists by this tester. And that means 1 out of 31. It means that there's only a 3.2% chance that the positive test is actually a terrorist. So this shows what's called the base rate fallacy. The base rate is that there's such a small percentage of terrorists in the building. So if you have a probability that's really low, and then you're trying to do some testing to identify members in that particular category, whether it's a terrorist or it's a person with a particular disease, even if you have a high degree of accuracy or predictability, like 99%, it's still going to give you enough false positives relative to the total amount to mean that the probability of that person or whomever being in that category, in this case of a terrorist, is so small. A 3.2% chance that the positive test is actually a terrorist, even when we have 99% accuracy. So this is a paradox where we think, how in the world can that be true? Well, I'm going to show you how. I'm going to show you how to navigate the mathematics of this. This is our conditional probability formula that we've come to know and love. All it means is the probability of A, some event, given that we know B is true, is the probability of A and B divided by the probability of B. If you don't remember that well, you can go back to the last video, CT-4, and I did lots of examples of that. So what are we going to do with this? Well, we're going to bring this into the context of disease testing. And there are 2 important vocabulary words with disease testing that you need to know: sensitivity and specificity. So when we do disease testing, we are interested in being correct, but we're also interested in what kind of corrects and what kind of incorrects we have when we make a diagnosis. So the sensitivity of a test is the probability that a person tests positive given that they have the disease. So the sensitivity is the test's ability to correctly identify someone with the disease. However, the specificity of the test, make sure you write these down, it'll be on our test. The specificity is a different way to be correct, and that is the test's ability to tell someone without the disease that they truly don't have it. So the sensitivity and the specificity of a test are two names for correct results. Someone has the disease and we correctly identify it. Someone doesn't have the disease and we correctly identify that they don't have the disease. The two options for types of errors that we can have would be a false positive. So that just means the test says someone is positive for the disease, but it's not true. Or a false negative. So we tell someone you don't have the disease, but it's actually wrong. You actually do have the disease. This is actually a pretty cool video. If you want to, I put the link to this video, it's YouTube, on our Foxtail page. It's about a 12-minute video. The guy goes through a car alarm example, and he talks about taking a car alarm that has a particular sensitivity for going off, and you can turn that sensitivity up or you can turn it down. So if you think about a car alarm, if you turn the sensitivity up because you don't want your car to get broken into, then maybe a big truck drives by your car and it kind of startles the car and the car alarm goes off, but it was a false alarm. It was incorrect, right? Or maybe a bike rides past or something happens that isn't a threat to your car, but your car alarm goes off because you've tuned up the sensitivity because you really want to make sure that no one breaks into your car, steals your stuff, steals your car. But that means that if you tune the sensitivity up, you get lots of false alarms. And if you get tired of having false alarms, then you could turn the sensitivity down. But that means that even though you wouldn't get so many false alarms, a careful criminal might be able to break into your car. So he talks about that, and I think it's pretty interesting. He does a good job. And he draws this little diagram. He draws a car with a little alarm right here and a little gauge for turning the sensitivity up and down. So then he talks about, he's trying to move you toward the possibilities with disease testing. So he's got disease here, and he's crossing that with testing. And he says, so you could have the disease, that's the plus here, and you could have a positive test, which means you're correctly identifying that a person has a disease. And then, or you could not have the disease, that's the minus, and you could have a negative test, and that means we have a true negative right here. And the errors are here and here. So right here, we've got the person does not have the disease, but the test says they do. So that would be a false positive. It's a positive test. And over here, this is a negative test, but they actually have the disease. So that would be a false negative. So it kind of talks about the advantages and disadvantages in a car alarm for tuning the test toward, I guess, whatever interest that you might have. What we're going to do, and this is a really important slide, you may want to take a picture of it, because all of the problems that we're going to navigate, you can use this, it's called a tree diagram. And what you might notice with the chart that we just looked at, as well as this tree diagram, it's exactly the same chart and exactly the same tree diagram as when we looked at Pascal's wager. So it's just possibilities. And we'll be looking at some COVID tests in a little bit. But so the idea is you either have COVID for real or you don't have COVID. If you have COVID, then your test could be positive or your test could be negative. If you don't have COVID, then you could have a positive test or a negative test. So these are all the possibilities. And notice I've labeled this up here, this positive test when you have COVID. That's a correct thing. And the probability for this is called the sensitivity of the test. That is when you have a correct diagnosis of COVID or whatever it might be, HIV or any other disease. Down here, you see a correct, this is called the specificity of the test. That just means you don't have COVID and the test is negative. So you've made a correct diagnosis. And then these two middle areas are the errors, right? If I have a negative test, but I'm on the COVID branch, that's a false negative. So you actually have it. Or if you're in this branch, you have no COVID, but a positive test, that's a false positive. Now, keep in mind that the more sensitive we make the test, think about the car alarm, the more sensitive we make the test, the more false positives we're going to get, because there's going to be a truck driving by the car and the car alarm is going to go off, but it's not really a thief. So this number right here, if we want that to go up, this number right here is actually also going to go up. But because these two things are opposites, it's going to force this number to go down. So there's actually an inverse relationship between sensitivity and specificity. In other words, if we want to make sure that we get all of the people with the disease correctly diagnosed as having the disease, we have to make a sacrifice there, because this number is going to go down. We're actually going to have more false positives, which means we're going to not correctly identify those that don't have the disease. So you have to consider all of these possibilities when looking at not only the scenarios, but the odds of the scenarios. And that's where this base rate fallacy comes into play. In the video on the car alarm, the guy does a pretty good job, I think, of kind of drawing this graph, this shape right here. And this represents patients without a disease. And then this other one represents patients with a disease. And with these tests, a lot of times they're not just binary. They're not just you have the disease or you don't have the disease. There's a numeric threshold that you get to set, kind of like setting a car alarm's sensitivity. So what he does is he goes in the video and he says, if you set the sensitivity down here, then all of the patients with the disease will be found. Like there's not going to be anybody with it that you don't find, but a whole bunch of patients without the disease are actually going to be diagnosed as having the disease because the threshold is set right here. And on the opposite end, you could set the threshold right here and make sure that everybody without the disease does not get identified as having the disease, if this is the disease threshold. But then there's a whole bunch of people in here with the disease that don't get correctly identified as having it. And he makes the case that this is kind of a fair place to be, where these two curves intersect. And in that case, some people have the disease but don't get diagnosed. That's over here. And other people, this would be like the yellow curve, actually do have it but get diagnosed, do not have it, sorry, but get diagnosed as having it. So if that makes sense, great. If it doesn't make sense, you can watch the other short little video. He does probably a way better job than I did of explaining it, but it's all interesting. This is a slide that I think kind of explains the idea again. Like sensitivity of the test is really the number of true positives divided by the number of true positives plus false negatives, which is really just the total number of individuals with the illness. So we just take the number of correct positives out of the total number of people that actually have it. But I think my way of calculating these problems will be a little bit easier. So if these definitions help, that's great. But I don't know that they're really going to help a lot for your calculations, because we're going to be given probabilities. All right, so we'll make a tree diagram. It's going to basically look like this every time. Generically, this will be having the disease. It's cancer, and then it's HIV, and then it's COVID, or whatever. And then down here, there would be the opposite, not having the disease. And what we'll have is we'll have a probability. So in this particular problem, the probability of a person having cancer is 0.001. So 1/10 of 1%. This is called the base rate right here. And the base rate fallacy happens when this number is especially small. But notice that this number and this number, since we're talking about opposites, they add up to 1. So if this is 0.001, you can always figure this one out by subtracting the other one from 1. Same thing happens over here. You have cancer. The sensitivity is always this branch. The sensitivity of the test is 99% chance of correctly identifying the cancer, which means that this is 1%, because we have a situation where it's an either or. The test is either positive and correct, or in this case, negative and incorrect. Down here, the bottom branch is the specificity of the test. 95% means that the other one is 5%. So you're not going to be given all these numbers. You're going to be given 3 of these numbers, and you'll have to find the other 3. but they just add up to 1 every time you break a branch. The other thing that you're going to be interested in is you're going to be interested in the probability of a person having cancer, and remember our operator and is times, and then having a positive test. So the numbers that you see over here, this number is simply 0.001 times 0.99. And this number represents the probability of a person having cancer and getting a positive test. This number right here is 0.001 times 0.01. And that's not going to happen very often, you can see. So every time you see a number over here, it's really just the branch multiplied, the branch probabilities multiplied together. So how would we calculate the probability of cancer given a positive test? Well, if you remember our formula, the probability of A given B is the probability of A and B divided by the probability of B. So I really need the probability of cancer given a positive test, and a positive test divided by the probability of a positive test. I'll talk through this, but we'll do it on the whiteboard in just a minute. Look at cancer and a positive test is this branch. So for this probability, this number will be the numerator, and we will divide it by the probability of having a positive test. But there's 2 ways to get a positive test. This is a positive test outcome, or you could have a positive test this way, no cancer and a positive test. So actually the calculation for this probability would be 0.00099 divided by 0.00099, or means plus. Remember, our or operator means plus. I'm going to have to take that plus this other positive test in the denominator, which we'll write out in just a minute. Well, actually, I think I'm going to do 2 examples just like that. So that was just for talking through it. But let's do this. I just got this out of a book. So it said for a particular HIV test called the Elias test, the base rate is 0.001. That means this is kind of the percent of people in the population that have HIV. That's the base rate. The sensitivity of this particular test is 98%, so that seems pretty good. There's a 98% chance that if they have it, they find it with the test. And the specificity is 94%. Remember, as this goes up, this goes down. So 94% would be the probability that you correctly identify a person as not having it when they don't have it. And what will we be interested in? Of course, the probability that we actually have HIV, given that the test is positive. And then, of course, the probability that we do not have HIV, given that the test is negative. So I'm actually going to stop the sharing, and I'm going to take you to my whiteboard so that we can navigate this. Pretty much always, this is the way our picture will look. So we've got D is the disease. In this case, it's HIV, but I'll keep the same table up for a COVID test scenario in a minute. And then in D is no disease. So notice we've got, excuse me, the base rate is 0.001, and I'll write base rate here. So whatever the base rate is, it's going to go here toward the disease. And the results will be more shocking as this base rate is smaller. So keep that in mind. As this base rate gets larger, then the results are still surprising, but not as shocking. And remember that the 2 branches, either a person has the disease or they don't have the disease. So you should be able to fill in this probability, in this case 0.999, because those 2 add up to 1. The specificity of the test is 94%, so this would be 6% right here. And if we've got a sensitivity of 98%, then we've got a 2% branch here, because these 2 are opposites, right? Disease, positive test is 98%, so negative test would be 2%. So there's negative test, positive test, negative test. And anytime I want a scenario, a probability of a scenario, I just multiply the probabilities on the branches. If I want to know what's the likelihood of having the disease and getting a positive test, I just take 0.001 times 0.98. But what we're going to be after, pretty much what we're really mostly interested in, is the probability of having the disease given that your test turned out positive. So that's what you want to know, right? You're like, I just got a positive test. Do I have this? And remember, the formula for conditional probability is the probability of this and this, D and positive test, divided by the probability of the thing that you know to be true. So this is just going to be the multipliers of the branch. So in this problem, it's going to be D and positive test. That's going to be 0.001 times 0.98, 0.001 times 0.98, divided by, this is kind of an interesting part, whatever appears in the numerator also appears always in the denominator. And that's because that will always be one of the ways to get to a positive test, right? I get to a positive test by having the disease and getting a positive test, or remember our or operator means plus. I can get to a positive test by having no disease but a positive test, right? So false positive. So I also have to multiply the 0.999 by the 0.06. So in words, this means the way to get a positive test would be to have the disease and have a positive test, and means times, or means plus, to not have the disease and have a positive test. Well, what's really interesting is when you type this into your calculator, and when you do, make sure you put parentheses around the denominator. The numerator doesn't care, you'll be fine with that. But this turns out to be, I just did it, 1.6%. Look at this. 0.016. Now that should be shocking, actually. You think about this. What does that mean? That means this is the probability of actually having HIV given that your test is positive. Is that crazy? So if you get a test back that says you have HIV, you should say it's very, very improbable that I actually have it. So this is kind of weird. We're like, why would you even use this test? Well, I think the justification would be that this particular test, this Elias test, is a filter test. And if you actually calculate this, the probability of not having the disease given a negative test, no disease given negative test, and of course that would just be no disease and negative test, so it would be 0.999 times 0.94 divided by the ways to get a negative test, which would be that times that, plus the other way to get a negative test would be that times that. Well, if you navigate that, it actually turns out to be essentially 1 or 100%. So here's the justification. If this particular test, which is probably cheap and fast, if this test says you don't have the disease, then there's pretty much a 100% chance that you don't have the disease. However, if this test says that you do have the disease, then you probably don't. There's only a 1.6% chance that you do have it. So it's probably a filter test that's fast and cheap, and it eliminates a whole bunch of people from having to do anything else because their test comes out negative, and their test comes out negative, and the likelihood of them not having the disease is basically 100%. It eliminates having to test them again. But most likely what you'd want to know is you take the people that did test positive and you give them another test that's probably more costly and time consuming. I think there's one called the Wechsler test for HIV. So this is probably a filter test, which doesn't mean it's not useful because it eliminates us having to retest all the people that got a negative result. So let's do another problem. I thought that we'd all be interested in COVID or sick of it, one of the two. So I try to find some numbers here. And that wasn't easy. So I had to I just picked some conservative numbers for this problem. I didn't want extremes, but I'll tell you what I found. So I'm going to erase these HIV numbers. Okay, so same chart, and we'll still be wondering what's the probability of the disease given a positive test, because that's what everybody wants to know, right? But we'll do COVID this time. And there are several different tests for COVID, but I think that the PCR test is a pretty popular one. So it's trying to figure out the base rate, like what probability goes here, what percentage of the population actually has or has had the disease. And there were a lot of different numbers online to pick. Remember, the bigger this number, the less shocking the results will be. So the number that I looked up as of February 2021 had it was about 7% of the population that it said had the disease, which means we would have 93% of the population without the disease. And of course, there were people arguing that this should be higher because a whole bunch of people haven't tested positive but have had the disease. And then there were people arguing that this number should be lower because it's been shown that the disease test yields a whole lot of false positives. So I just picked a number that it was kind of high for this problem, but I didn't want to pick something too low and make it shocking. I feel like I picked some numbers in this problem that were in the middle of people's predictions. All right, so the sensitivity of the test, this PCR test is ratcheted up to be very, very, very sensitive. And really, I think 98 was the lowest sensitivity I saw, up to 100. And 99.5 or 99 were the two numbers. So the numbers for here were pretty much all in this like 99% range. So let's say we've got a test that's got a sensitivity of 99%. And of course, that means that if someone has it, there's a 99% chance that this test will find it, which means there's a 1% chance of having the disease and having a negative test. Then I was looking for different specificities, and boy, the numbers were all over the park. They were down from 70% up into the 90%. So I think I picked 80%. And on your homework, I'm going to actually give you some different numbers to try so that you can see the results of different possibilities. Of course, if this is 80%, then this is the opposite branch, which means it's 20%. And now we can do our calculation. Of course, we want to know what is the probability of having COVID, the disease, given that your test is positive. Everybody wants to know that. So that would be the probability of the disease and a positive test divided by the probability of a positive test. So here we go. The probability of having the disease and a positive test, remember, and is a multiplier, so 0.07 times 0.99 divided by the probability of a positive test. But notice, you can get a positive test this way. You can also get a positive test this way. So there's this branch, and or means plus. And how do I navigate the branches? I would have to have the disease and a positive result. So I multiply those together, 0.07 times 0.99. Or means plus, there's another way to get a positive test. And that would be not having COVID and having a positive test. So that would be 0.93 times 0.2. 0.93 times 0.2. Yeah, I think I typed that into my calculator. Yeah, it turned out to be 27%, which actually should be pretty surprising. I'll write this down. The probability of the disease given a positive test. And remember, these are pretty conservative numbers. So I just looked on the web, and I picked numbers in the middle of what people were estimating. But even if I pick just regular old conservative numbers, you can see what's really happening is the likelihood of having the disease, given that your test is positive, under these relatively conservative conditions is 27%. That means if you've tested positive for COVID, under these conditions, there's only a 27% chance that you actually have it. So that should be pretty surprising. And if you run the other thing that people would care about, the probability of not having the disease, given that your test is negative, right? So negative test. It'd be the same kind of calculation. It would be no disease and negative test. So I just do 0.93 times 0.8 divided by the way to get a negative test would be here, or, which means plus, here. But you basically get 100%. It's essentially 1. So if your test is negative under these same exact conditions, you can be sure that you don't have it. But if your test is positive, there's only about a quarter or just over a 1/4% chance, not a 1/4%, but 27% chance that you have it, which should be pretty shocking, pretty surprising, pretty interesting. This is a paradox. It's a numeric paradox, and people think one way, but they don't understand that the base rate has everything to do with all of this. And that's why when people think a certain way, they're like, well, I got a 99% sensitivity. This is a great test. This is amazing. Then they're shocked when they actually do the mathematics with the conditional probabilities and find that under these conditions, the likelihood of actually having it, given that you have a positive test, is 27%. No one seems to be talking about that, but it's a mathematical paradox. Let me just walk you through a few more slides in my PowerPoint. You may want to go back and look at some of these examples. Pretty much you can guarantee you're going to get something like this on your next exam. And most of the problems are pretty similar. So once you've done a few, you've probably got it. Okay, let's see. Oh, shoot, something just happened. What happened? Trying to click through my PowerPoint, that's all. Is that too much to ask? Yeah, so that's the problem we just did. You can write down those pieces of data if you want to. As I mentioned, the numbers in the previous problem were conservative estimates, which means, of course, under those conditions, if a person has tested positive for COVID, they actually probably didn't have it, which is weird. But on the homework, what I'm going to do is I'll change the base rate, I'll change the sensitivity, I'll change the specificity, so that you can look at alternative possibilities and alternative probabilities, which will be really interesting and useful. I also thought that this was useful. This is our world news, I guess. The World Health Organization released this memo on the 20th of January, Inauguration Day, as it were. And it's really interesting. I haven't seen it anywhere but one place, and you have to go into their archives, but here's the website if you want to look it up. So this is a memo sent out to the doctors that are performing the COVID tests. And I'll just say that it's kind of interesting because I remember I started teaching in 1994. And in 1994, I taught an SAT prep class. And it was really important that all of us teach SAT prep classes that year, because what had happened was SAT decided to change the test. And so the SAT exam before 1994, like when I was in high school, was a skills-based test through calculus. And then in 1994, they changed it to like a problem-solving based test up through high school geometry. And so you can see that it completely changed the way that we helped students prepare for the exam. But also, if you had a 1993 exam versus a 1995 exam, they're still using the same scores back then, but yet it communicated something completely different as far as the information. So you get a score in 93, you get a score in 95, you think they're comparable. They're not. It's apples and oranges. When you change the rules, that completely changes or ought to change the interpretation. So here's what it says in the archives of the World Health Organization. Notice, and I don't understand all of this stuff. I'll just explain a little bit of the things that I noticed. So this is a memo, January 20th, 2021 on SARS-CoV-2. Purpose of this notice, it supersedes World Health Organization information notice for IVD users. Okay, so this is something new that they're telling us. IVDs must read and follow the IFU. Wow, that doesn't sound very good. Carefully to examine If manual adjustments of the PCR positivity threshold is recommended by the manufacturer. So the PCR test is a COVID test, and it's a positivity threshold. So as I mentioned before, it's not necessarily a yes or no. You have it or you don't. There's a numeric value called a CT value, and there's a sensitivity that you set the test at, just like a car alarm. And we're looking at, where should we set this sensitivity, the threshold? We're looking at this, and it says a careful interpretation of weak positive results is needed. The CT threshold to detect a virus is inversely proportional to the patient's viral load. That just means that as the CT number is higher, the viral load is lower. So an inverse relationship, when one goes up, the other goes down. Where test results do not correspond with the clinical presentation, a new specimen should be taken. In other words, you might want to test again and retest using the same or different technology. So this might be like the Elias versus the Wexler HIV test. Like this particular test, the PCR test, we're not sure that the thresholds that are being used are giving us accurate results. As disease prevalence decreases, the risk of false positives increase. This means that the probability that a person who has a positive result is truly infected with SARS-CoV-2 decreases as prevalence decreases. I think, and maybe a person who's more of an expert than me, I think what is being said here is like, hey, this particular test, if you look at the CT numbers and the thresholds that have been used, it may be that there have been a lot of false positives. So we need to carefully interpret and maybe even try a different test. And what I feel like is kind of interesting, and maybe I'm wrong, I don't know for sure, but it seems like what they're saying is maybe you should reevaluate the threshold or the sensitivity of this test. And what have we seen? We've actually seen a dramatic decrease in COVID cases since this memo came out from the World Health Organization. Now, do I know for a fact that that is because of the memo and that people are interpreting the results differently? I don't know that. I do have a friend who's a doctor, and he said that he was not using the CT threshold recommendations from the beginning. And so his COVID cases, he was actually determining that people had less positive results because his threshold that he was using was different than the one that was recommended earlier. And now they have the freedom to I guess, change the threshold. But again, I don't know, but it seems like the rules have changed, and voila, surprise, surprise, the statistics are changing. So it might be, though, that nothing has changed, or not as much has changed as it appears, because numbers that previously would have been interpreted as positive results now are being interpreted as negative results. So, and it could be because of what we just looked at, Bayes' theorem, where you do the conditional probability, and it's like under these conditions that most people are assuming, the likelihood of actually having COVID given a positive test isn't very high. So, but no one seems to be talking about that except me. I'll probably get in trouble for it, but how about this? And this is a strong assertion, and I don't know if it's true or not, but I read it and I think it'd be worth looking into. It says, contrary to expert predictions and media headlines, the lowest death rates from COVID-19 are in the poorest countries with no masking, no social distancing, limited medical care, no ICUs, but easy access to hydroxychloroquine and chloroquine. So you can look that up if you want. I don't know if that's true or not, but it would be really interesting to see some of these poor countries that have not had the resources that some of the more wealthy countries have had, and what they've had to deal with, and how they've dealt with all that's gone on, and to see the actual results. That would be of interest to all of us, I'm sure. All right, if you want to practice, here's another problem that you can practice. I'll have a worksheet for you. Hopefully you found this interesting and not too complicated, but it's certainly relevant, and it is a good illustration of the base rate fallacy. I will look forward to seeing you soon.